Here's where we start. Solving quadratics over the complex numbers. Here's a reminder of a couple of things to do with quadratics. So in year 10, you did quadratics in mathematics, and you learned to factorise quadratics in order to solve them. And that included monomic and non-monomic quadratics, so hopefully you remember that. And you learned to complete the square, which was all this stuff. And this is the foolproof way, if you can do that for all of them. And the quadratic formula, which is just a generalization of completing the square, is also a foolproof way and will always work. This doesn't always work. Well, it does always work, but sometimes you've got to work out that the square root of 3 is one of the roots or something like that. So these are good. Factorising is hard. I'd still expect you to look for factorising opportunities, but I wouldn't expect you to look that long for factorising opportunities. Point 2 and 3 would be the way to go. So what I want to do is run through a quick reminder in example 1 of how to solve quadratics using those 3 methods. So I'm going to pause the video now and give you a minute to solve that quadratic using as many of those 3 methods as you possibly can, and then we'll run through it. I've resumed, ladies and gentlemen. So 2x squared plus 13x minus 7. I've just resumed. I'm going to carry on and do it, and I'll show you if it's it. Okay. So to factorise and solve this quadratic, the first thing obviously we're going to do is factorise, and this is the long non-monic way. If you know this can be factorised, there's an easier way of doing it, and that is to recognise a 2x, 1x in the brackets and use a bit of logic. But for now, we're basically looking for 2 numbers that add to give 13 and 2 numbers that multiply to give negative 14. And that negative 14 came from A times C. So this is my process might be worked out a little bit differently, but whichever teacher you had in year 10 will have done essentially the same process. And so the 2 numbers that multiply and add to give 13 are 14 and negative 1, 14 and negative 1. And so we get this. And this is the method that I learned recently. 2x plus 14 over 2x minus 1 divided by an extra factor of 2. So we're leaving in 2x and 2x, and as you know, that would make 4x. So we have to divide it by 2 to cancel that out. And then, you might not remember this process, but hopefully you remember partly. That 2x plus 14 can be factorised to be 2 times x. So this is being 2 times x plus 7, 2x minus 1, all over 2, and that's equal to x plus 7, 2x minus 1. And therefore, x plus 7, 2x minus 1 equals 0, which gives x is equal to negative 7 or a half. Excellent, and that's good, but remember we do have tech active and tech free exams. Any questions on that method? That's the non-monic method. There's also a monic method that works just as well. You may or may not be able to factorise. I probably expect you won't be doing that necessarily in your exam. But that's number 1, and that is factorising. Let's do the second. Okay, so Max, I'm just going to carry on and do this on the board without you talking at the top. Is that all right? Excellent. Completing the square, secondly. You had a go at this, most of you, and you're making some good progress. But here's the full complete method. 2x squared, remind me, 13x plus 13x minus 7. And if we want to complete the square on this, I'm going to put in equals 0, and we can complete the square as part of the full solution of the equation. If you want to complete the square on this, the easiest way is to take that 2 out of the factor. It does create some fractions, but taking 2 out of the factor takes away the non-monic nature of the quadratic. I'm going to leave the negative 7 there. I'm going to take the 2 out as a factor of x squared plus, and then I get 13 over 2x minus 7. Now I need to halve this square and add it on. I'm creating a perfect square. So I get now 2x squared plus 13 over 2x, and I'm going to change that 13 over 2. I'm going to write it down as this. 2 times 13 over 4x, and then in red, I'm going to add 13 over 4 squared, I'm going to subtract 13 over 4 squared. I'll close the brackets and subtract 7, and that equals 0. It still equals 0. So as you can see here, I've not changed 13 over 2. I've just written it down as 2 times 13 over 4. And I've not changed this. I've just added and subtracted a number that's the same. It's just quite a complex number. We don't have to worry too much about that. Now I'm going to write this as 2 times, and this bit here is now a perfect square in the form x plus a squared is equal to x squared plus 2ax plus a squared. So you can see that the x is x, the a is 13 over 4. We've got x squared plus 2 times a times x plus a squared. That's the design. We've designed to do this. So it's very deliberate. It becomes x plus a, which is 13 over 4 squared. This bit, though, is left over, so we have to expand that out of the brackets. That means that that bit has to be multiplied by 2 that's outside the brackets, and then have the subtract 7 applied to it. So I get plus 2 times negative, and 13 over 4 squared is 169 over 16. This pen, 16, and then minus 7 equals 0, and 2x plus 13 over 4 squared. 2 times 169 over 16 is 169 over 8. 7 becomes 56 over 8. Are we happy with that? Negative 169 minus 56, what's that? 225 minus 225 over 8 equals 0. Sorry?
You silly duck.
No, because the 2 times that becomes 16, yeah? That becomes 8. And then that becomes 2x plus 13 over 4 squared equals 225 over 8. Then I divide by 2, give me x plus 13 over 4 squared equals 225 over 16. And then I take a square root of both sides. X plus 13 over 4 is equal to 15 over 4. And it could be plus or minus that. When I take the square root, I get the plus or minus. And then I add 13 over 4 to both sides to give me x is equal to, if it's positive 15 over 4, then it becomes 15 plus 13, which is 28 over 4. Oh no, it's a subtraction, sorry. If it's positive 15 over 4 minus 13 over 4, I get 2 over 4. And if it's negative 15 over 4 minus 13 over 4, I get negative 28 over 4. That's equal to a half, or negative 7, which is thankfully what I got using the other method over here. Well, it's long because there's fractions in it, so it can be shorter. And of course, the third method, very quickly, and the third method is usually the quickest. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, 2, 13 and 7. So a equals 2, b equals 13, c equals 7. And I get, are they all positive? No, negative 7. I get negative 13 plus or minus the square root of 13 squared minus 4 times 2 times negative 7, and all over 2 times 2, which is 4. And you'll see some numbers pop up here that you recognise. Negative 13 over 4 plus or minus the square root of 225 over 4. And that equals a half, or negative 7, guaranteed. So you get the same answer. My pen's being really funny, so there we go. Any questions on any of those methods? Perhaps you could just sit down for me. Would that be all right? It's been quite distracting so far already. So I would suggest that you know all three of those methods. I'd suggest you do some of the questions using each of those different methods. I would anticipate that in an exam situation, you might get a question you can recognise as easily factorisable, and therefore you do that, because if you can factorise and you can spot that, it is the quickest method. And if you don't get that, you'll probably use the quadratic formula, but you may be asked to use completing the square. It's noted in a dot point. I'm going to avoid asking you that in IA2, but I can't guarantee anything about the external exam. So know how to complete the square. I think so, yeah, if it's a dot point. Because otherwise, in this particular case, you'd just always go to the quadratic formula, wouldn't you? So I would imagine they might do that. Okay? So let's solve this one over C. Now, if it says over C, or if it's in a specialist maths exam in IA2, it probably has complex roots. Expect that to happen. And if it has complex roots, you're not going to be able to factorise it. Not very easily. But that factorisation process is still important. So in this case, as soon as it says over C and as soon as it's in the specialist maths exam, I'm going to go to either square or to the quadratic formula. So let's say I go to the quadratic formula. I get Z is equal to negative B, which is negative 4, plus or minus the square root of B squared, which is negative 4 squared, minus 4 times 1 times 5. Please note that I put the negative 4 in a bracket to make sure I don't end up with negative 4 squared is negative 16. All over 2, and I get this, 4 plus or minus the square root of 16 minus 20 all over 2, which is 4 over 2 plus or minus the square root of 4, and by 4 I mean negative 4, over 2, and that's equal to 2 plus or minus 2i over 2, which is just equal to 2 plus or minus I. Now this leads us to our next thing. There are two solutions for Z. So there's a couple of things here that I want to show you. First of all, and these are not asked in a question, it just says solve, so we've got full marks there. What does Z squared minus 4Z plus 5 look like in factorised form? Two Z plus I. That's it. That's it, perfect. So you remember, if we have a quadratic, ax squared plus bx plus c, this will be equal, actually let's remove the a, let's just make it monic for simplicity. This will be equal to x plus alpha and x plus beta. I've actually made one mistake, my apologies. So this will be equal to x minus alpha and x minus beta, where alpha and beta are our roots. They're our solutions to the equation. So in this case, that shouldn't be a plus, that should be a minus, because we subtract the roots. But pretty much spot on. So we put our roots in here, but this is still slightly, well actually this works perfectly, but technically it's easier if we just put the roots in brackets here. So we recognise that Z minus 2 plus I and Z minus 2 minus I. But the way this is formed, if you expanded the bracket, you get the same thing anyway, so it doesn't matter. So that's first of all the factorised form, and if we find the roots, we can write the factored form. But as you can see, working out what this is from that would be quite hard. The second thing I want to talk to you about is the fact that there's a special relationship between the two roots. Can we see what that is? The conjugate. So one root the other, and we've talked about this before, but let's talk about it again. The first root is the conjugate of the other. So what we say, therefore, is if W is a root of some polynomial Z, then W bar is also a root of PZ. So P of W will equal 0 and P of W bar will equal 0. Only in special circumstances, which I'll talk about in a second, but you can see why that happens. If you go down to here and have a look at our solution, as it forms, the complex part of the solution is always here because it always comes from the square root. So as we go down here, you'll see that's the complex part, that's the real part. It's always the real part plus or minus the complex part, which is our definition of a conjugate. So you can see where that comes from in that form. Now the conjugate root theorem doesn't hold in all cases, and I will talk to you about that, but maybe not today. Example 3, which is basically the last thing I want to talk to you about today, is show that 1 plus 2i is a factor of that. Write f as z in vector form. Determine a polynomial of real coefficients that has 3 minus I as a solution. How many such polynomials exist? I'm going to leave that one, part C, as homework, and you'll come in tomorrow morning, hopefully, with a solution for me, but we're going to play it like categories. So I'd like you to come in tomorrow morning with a solution that you believe is unique that no one else in the class has. That's how categories work. Okay, so I'll give you a hint. The second part of this question is how many such polynomials exist? The answer is an infinite number. You just need to come up with one. Surely out of an infinite number of polynomials, you can come up with one that's different to everybody else's, but I don't know. We'll see how it goes. Question A though, show that 1 plus 2i is a factor of z squared minus 2z plus 5. How do we do that? Factorise, no. Derive, no. Divide, maybe, but it's hard. Conjugate root theorem could work, but it's probably about as hard as, dividing. That's kind of like factorising, which is, it will work, but it's a long way. That's on the wrong path. Factorise will work, but it's a long way. Can I give you a hint? Go back to term 1 math methods. How could you tell if a number was a root to a polynomial? So I'll give you another hint. Remainder theorem. Remainder theorem. F of a root has to equal 0. Okay. F of 1 plus 2i should equal 0. If it's a root, indeed, embarrassingly for you, it is. If anybody's wondering, that's Max Brown being a goose. F of 1 plus 2i equals 0. That's what we need to show. If we can show that, then it is definitely a root. So let's do that. 1 plus 2i squared minus 2 times 1 plus 2i plus 5. That's equal to, if I square the 1 plus 2i, I get 1 squared plus 2 times 1 times 2i plus 2i squared minus 2 times 1 minus 4i, because that's 2 times 2i, and then plus 5. That's equal to 1 plus 4i, and then plus 4i squared minus 2 minus 4i plus 5. Minus 4i plus 4i cancel out. 1, 5 and minus 2 leave me with 4. And then plus 4 times I squared, which is negative 1. 4 minus 4, which is 0. So that is indeed a factor. Okay, now B. Note here that if the question says, show that this is the root, and the second part says, write it in factored form, factorising in part A is probably not going to be the right way to go because that wouldn't be part B if that was the case. So f of z in factored form is equal to, I'll do the first part, z minus 1 plus 2i to quadratic, so there's only one more factor. Excellent, the conjugate. Excellent. That's it, that's factored form. So I'm going to leave you now. You've got 11 minutes left. You can do some of the work or you can do part C.